Hello, everyone, and welcome to the VaNTAGe seminar. So today we're continuing our series of talks on rational points on higher genus curves. And we're very happy today to have Netan Dogra, who's talking about rational points on curves via algebraic cycles on surfaces. And Netan, is it okay for us to record this talk?
Yep, absolutely.
Oh, great. And everyone, feel free to ask questions during the talk. Wonderful. Please feel free to get started.
Great, thank you. Thanks very much for the opportunity to give this talk. It's I'm really pleased that to have the chance to speak here and that you're organizing this series of talks on this topic very dear to my heart. And also, it's very nice at the moment to have the chance to give a talk online from the comfort of my office. So, what I want to talk about is some methods for finding rational points on curves, some kind of new ideas related to this non-abelian Chabati method. And I've given this talk before with the title Non-abelian Chabati 5, the Jacobian Strikes Back. Um, this is the second time I've given this talk in a series of talks, and unfortunately both times I ended up giving the fourth talk. Um, but yeah, I'll try and explain the sense in which the Jacobian strikes back later in the talk. So I'm not going to assume that everyone has fully internalized everything that has been covered in the previous talks in this series. Um, but I'm also not going to spend so much time going into the kind of foundations of the theory. As I'll kind of recall a bit later, non-abelian Chabati is something which gives you these sets of p-adic points, xqp subscript u. The u is some quotient of some unipotent group over qp. And two big questions in the theory are, first of all, when you can show that this xqpu is finite, and secondly, how you compute it. Um, and I want to explain some ideas to try and turn these questions into really kind of computational questions. And the computational problems you end up having to solve are kind of related to explicit methods for algebraic cycles on, well, they'll end up being on X or on products of X, or actually sometimes on some other varieties as well, perhaps. And more generally, kind of generalization of algebraic cycles, mixed motives and higher Chow groups and things like this. And yeah, I really want to advertise that I think these subjects are very kind of ripe for computational experimentation because there are so many conjectures about what these objects look like, and so many predictions for the existence of certain relations between algebraic cycles and things like that. We don't know how to prove. I mean, we know so much less about how to prove these things than we do in the case of abelian varieties, and that's really a motivation to actually experiment with these predictions. So I feel like uh, computations with abelian varieties has been one of the kind of great success stories of computational number theory over the past few decades. And maybe this could be, I mean, so that I'll explain later, there's already been a lot of great computational work on these questions of mixed motives and algebraic cycles, but I think it's ripe for doing even more. And I noticed recently that actually, very exciting, there's going to be an Arizona Winter School next year about computational arithmetic geometry. I don't know that they're going to cover these kinds of questions, but it means that there are going to be kind of lots of brilliant young mathematicians working on computational arithmetic geometry, which makes it even more kind of ripe for experimentation. Okay, so I'm kind of going to divide my talk into two, answering these two questions. And really what I want to do is have some kind of non-abelian generalization of things we know how to do in the Chabati-Coleman method. So let's recall how the Chabati-Coleman method works, is that you have a curve X, some nice curve X, and you think of it inside its Jacobian. And you assume the rank of the model vagrum of the Jacobian is less than the genus. And then that allows you to consider this intersection of the topological closure of the rational points of the Jacobian with the p-adic points of the curve. So there's a picture which I think um, you've seen before of that you could think of this like this is your curve and it's sitting inside your Jacobian over the p-adic points, which is some box, and maybe the topological closure of the Jacobian is some lines, one-dimensional space. Sorry, that's terrible writing. And then you get this finite intersection. So in this case, it actually just ended up being in size 1. Uh, you can then compute in practice. So how do you compute this in practice? So for example, how do you do this, say, for a hyperelliptic curve? It's mostly what I'll be talking about. Well, first of all, you need to compute the Mordell-Weil group. You need to compute the rank. Well, actually, yes, that's an important point. You don't really need to compute the Mordell-Weil group. You just need the rank, which is less information. And so, as I said, this is one of the great success stories of computational number theory is that we have pretty good algorithms for doing 2 descent on hyperelliptic Jacobians. And then you need to find, again, you don't need to find generators of the Jacobian, but you need to find a finite index subgroup of the Jacobian. Then once you've done that, actually, so then you have to do some kind of p-adic analytic computations to compute some Coleman integrals. That will give you this set XQP1, or this set of p-adic points which are killed by the annihilating differential. And then you have to get XQ from that, you have to do some sieving process, which is a very interesting story, but not really what I want to talk about. Really what I want to talk about is generalizing the first 2 steps, so the 2 descent and that lets you compute the Mordell-Weil rank and finding this set of generators that lets you actually compute the image of J of Q inside J of QP. So to explain that, let me just tell you a little bit about how the Chavati-Coleman-Kim method works. So we have some nice curve X of genus bigger than 1. And the Chavati-Coleman-Kim method gives you this decreasing sequence of subsets of the p-adic points. And the first subset of the p-adic points you get is exactly the one you get from usual Chavati-Coleman. And often the way that people phrase this generalization, and I've been guilty of this in the past, is to say that you get rid of the Jacobian. So I think also if you look at some great set of 2 short expository lectures by Bjorn Poonen from the Arizona Winter School a few years ago, where he talks about the Chavati-Kim method and also the Lorentz-Venkatesh method, and he emphasizes this perspective that we want to get rid of the Jacobian, phrase even classical Chavati-Coleman without ever mentioning the Jacobian. And I'll kind of say what the limitations of that are later. So what does this give you? Well, I mean, so the reason you want to do this is you want to be able to get finite sets of p-adic points containing the rational points when the rank is greater than or equal to the genus. And what do we know about this? Well, there's a theorem of Kim is much more general than the theorem which I've stated here, which says that, so I guess I'll move that up. It says that this set XQP2, so the next thing you get after Chavati-Coleman, is finite whenever the rank of the Jacobian is less than this number here. So yes, I'm going to use this notation quite a lot. VP of J is going to be the tape module of the Jacobian at some prime P. Actually, for us, most of the time, P will be 2. And then you tensor it with QP. So it's a QP vector space. It's a p-adic Galois representation. And there's a generalization of this theorem, which Kim also gives, which tells you that XQPN is finite whenever these certain H1Fs, which I'll talk more about later, have an appropriately small dimension. So a natural question then is, when does that happen? So, okay, before I get onto that, I guess you've already seen, I just want to make a little distinction. So in this talk, I'm going to be mostly talking about XQP2, and that XQP2 is often called, that kind of set you get from XQP2 is often called the set you get from quadratic Chabati. But quadratic Chabati is also often used to refer to slightly larger set of p-adic points. So on the level of fundamental groups, which I haven't discussed here, that corresponds to taking a slightly smaller quotient of the fundamental group. What's nice about this kind of larger set is it's the condition for finiteness is slightly more tractable than the one. Sorry, I'm going to scroll down here. I wrote down over here because it doesn't involve this thing, which is big mystery. Instead, it just involves this thing, which is the Picard number of the Jacobian, which is a really kind of geometric thing, not arithmetic. And so, yeah, the previous talks in the series that have talked about quadratic Chabati have talked about this kind of thing, but I'm actually going to be talking about this smaller set that uses a larger quotient. And I feel kind of partly responsible for this terminological confusion. So I'm going to try introducing some new terminology, which is that full fat quadratic Chabati is this set which kind of really is this a priori smaller set XQP2, and Dirac quadratic Chabati is the one that just comes from p-adic heights. So just to clarify, the Dirac quadratic Chabati, if the Dirac quadratic Chabati set is finite, then the full fat one is finite. I was quite pleased with this terminology, and so someone pointed out to me that's actually a bit of a mixed metaphor. So maybe Dirac quadratic Chabati should be something like semi-skimmed quadratic. I don't know. Anyway, I'm going to keep the terminology. And yes, I just want to emphasize, try and convince you, hopefully, in this talk that you might have heard a lot about the benefits of Dirac quadratic Chabati, but really, full fat quadratic Chabati is better for you. And hopefully, soon it will be something that it's really possible to use to find rational points in greater generality. So I said that you could prove finiteness of these sets XQPN whenever you can prove whenever you can bound the dimension of these crystalline Galois cohomology groups, or these H1Fs as I call them, of these Galois representations, which were essentially taken from taking tensor powers of the Tate module of the Jacobian. So there are these conjectures called the Bloch-Kato conjectures. Unfortunately, they're the Bloch-Kato conjectures which haven't been proved, not the Bloch-Kato conjectures which were proved. And they give a very precise prediction for what the dimension of these groups are. So it's actually, it's strange that these Bloch-Kato Selma groups are meant to be like generalizations of the Selma groups of abelian varieties. But it turns out that unlike Selma groups of abelian varieties, almost all of these Bloch-Kato Selma groups, you can predict almost exactly what the dimension is supposed to be in a kind of geometric way. There's no kind of arithmetically interesting invariant like the rank. That's the prediction anyway. So anyway, it gives you these predictions, like, for example, for a genus 2 curve, Bloch-Kato conjectures predict that the set XQP2 is finite whenever the rank is less than 4. XQP3 is finite whenever the rank is less than 12. XQP4 is finite whenever the rank is less than 33. And XQP5 is finite whenever the rank is less than 105. So if you found a genus 2 curve for which the Bloch-Kato conjectures couldn't prove that XQP5 was finite, then that would really probably be more interesting than actually being able to prove finiteness. I think I haven't been keeping up with the news about ranks of abelian varieties coming out of Harvard.
And are these
Yeah.
is it thought that these would be optimal, or that they could be widely bigger than?
Oh, you mean this rank inequality?
Yeah.
Yeah. So this, I would say that these are optimal for a generic curve. So there are various ways in which there could be curves of larger rank, which for which you could still prove finiteness. So, for example, in the Chabati-Coleman method, you could have a genus 2 curve whose Jacobian was isogynous to um, uh, E1 times E2, where E1 was an elliptic curve of rank 2 and E2 was an elliptic curve of rank 0. And then you would still have finiteness, but of XQP1, even though the rank was 2. And that's because you would basically just map your curve to this rank 0 elliptic curve. That would be what you get from Chevy-Coleman. So it turns out there are actually slightly more interesting ways that you can get finiteness of these XQPNs, which still satisfy this condition. So there was an example that Jennifer and I worked out. So you can take a curve. So I'm just going to write it here. Y squared equals x to the 6 plus a x to the 4 plus a x squared plus 1. So in this case, the Jacobian will be isogenous to E times E, where E is this elliptic curve x cubed plus a x squared plus ax plus 1. And it turns out you can actually prove finiteness of XQP2 even when the rank of E is 2, which would mean the rank of the Jacobian is 4, which wouldn't be true for a generic curve. I guess actually in that example that is explained by this inequality. But in the paper we give some examples which do go beyond this inequality. Yeah. Thanks. Okay, so I said that I want kind of computational methods for verifying finiteness of XQPN. And this is something which I think hadn't been thought about so much, maybe partly because we have these conjectures which predict the XQPN, which predict what the dimension of these Bloch-Kato-Selmer groups are. So, I mean, part of the appeal of non-abelian Chaboti is that it tells us that we shouldn't really have to do a 2 descent to work out the analogues of kind of ranks of the Jacobians. But given that we don't know how to prove these conjectures, maybe it would be nice to be able to have some kind of computational approach. So to explain how that computational approach might work, let me just look under the hood a little bit, these definitions of Bloch-Kato-Selmer groups. The Bloch-Kato-Selmer groups are global Galois cohomology groups of some p-adic Galois representation. And they're kind of supposed to be almost everywhere unramified. And then at v equals p, there's this slightly complicated condition of being crystalline, which says that when you tensor the Galois representation with this mysterious ring B Chris, which has a Galois action, you get a trivial Galois cohomology class. So to verify this kind of expectation, the expectations we get from the Bloch-Kato conjectures in examples, the big challenge is to have some kind of explicit methods to kind of compute the dimensions of these Bloch-Kato-Selmer groups. And ultimately, we want to get exactly the dimension predicted. And obviously, a priori, this is a non-trivial thing if you look at this definition, because B is a representation of the Galois group of Q into GLN QP. It's not something you can store on your computer. B Chris is also a priori, it looks like not something you can store on your computer. But actually, the situation is not so bad. So to kind of explain, before I explain one way that you can do this for some examples, let's kind of have a look at the archetype, the thing we want to kind of have a version of, which is the kind of really beautiful theory of 2 Selmer groups of hyperelliptic curves, which goes back, well, maybe I'll get the history wrong, but it goes back, I think, to work of Castles and Schaefer, Brown, Boonen, Stoll. So suppose I've got a hyperelliptic curve given by a polynomial of odd degree. So that's saying I've got a hyperelliptic curve with a rational bias stress point over a field K of characteristic different from 2. And I'm going to make a few assumptions which you really don't need, um, just to make it slightly simpler to write things down. So let's suppose that f is irreducible, and let's let k of alpha be the field obtained by joining a root. Then the Gabor cohomology of the two torsions of the Jacobian you can identify with this subgroup of the units of k of alpha modulo squares. So it's just the kernel of the norm map to k cross modulo squares. If you make this identification, what's even better is that you can actually describe exactly what the map is from points on the Jacobian to cohomology classes with values in J of 2. So if I have two k points, Z and W, I assume they're both not Weierstrass points, so they don't have the points at infinity or points with y coordinate 0. And there's this thing which is usually called the x minus t map, send Z minus W to this quantity here, which you can check is in the kernel of the norm map. And I mean, I should say that there are kind of big generalizations of this, the cyclic covers of P1. And there's also, I mean, the thing Kunin and Schaefer did really was actually explain the more complicated and more interesting case of where you don't have a rational Weierstrass point. I'll say a little bit more about that later. So yeah, we want some kind of analog of these kind of formulas. And so you can get analogs of these. Before I explain these, maybe let me just state some results, some things you can do with this. So the first thing you can do is you can verify the predicted dimension. So I didn't say that this quantity here, this one here, this is exactly the thing whose dimension you needed to, in this previous theorem of Kim, whose dimension you needed to bound to prove finiteness of x QB2. And this number 2 is exactly the number which is predicted by the Bloch-Carter conjectures. So we can verify this in this example of this genus 2 curve with Mordove rank 3. So this curve originally came up because there's a very nice paper of Bijot, Mignot, Sixek, Stoll, and Tengeli, where they find the integral points on this. And they ask the question of what the rational points are. And because it's genus 2 and rank 3, it's quite far beyond what you can do using normal Chabot-Coleman. So that's, and also I should say also, maybe I should have mentioned this one also has rho of j equals 1. So then another thing you can do, which doesn't involve actually finding the rational points yet, is you can look at genus 2 curves in the LMFDB of Mordel, where the Jacobian has Mordove rank 2, and then you can see whether you can prove that at least this set XGP2 is finite. So one interesting thing about working with these Bloch-Carter-Selmer groups is you can develop kind of 2 descent methods that will allow you to prove finiteness of XGP2, but unlike in normal Chabot-Coleman, they only work at 1 prime. And that's related to the limitations of our knowledge about algebraic cycles. So you can verify finiteness of XQ2 of 2 for, well, just under half of rank 2 genus 2 curves with a rational Weierstrass point. I think in the paper, I phrased it in terms of rank 2 genus 2 curves with exactly 1 rational Weierstrass point. And I think then, if I remember rightly, it ends up being just over half, which sounds slightly nicer. But as I'll say, since there have been work of Lee Berry, which improves this and removes some of these restrictions. Okay, so now I think if there are no questions, I'll go on to explain a bit about how 2 descent for Bloch-Carter-Selmer groups works. So I said the thing that was bad a priori about these Bloch-Carter-Selmer groups is that they involve an infinite amount of information. Actually, it's Not hard to see how you would try and replace that with a finite amount of information. What you would do is you would take a Galois stable lattice T inside your Galois representation V, and then you would try and, so you can similarly define H1F GQ of T. So what you do is you just take the pre-image of H1F GQ of V under the map from H1 GQT to H1 GQV. On the other hand, now you have a lattice. So basically, maybe it'd be clearer if I wrote down a couple of exact sequences. So you've got the exact sequence from T to V to V mod T to 0. And you've got the exact sequence from T to T mod PT. So then if you apply cohomology to these, this gives you a map from the Galois cohomology of T tensored with FP into the Galois cohomology of T mod PT or T tensor FP. And so you could try, and the nice thing about T mod PT is the Galois cohomology of that really is a finite object in some reasonable sense. So then you could try and come up with the definition of some kind of H1F GQ T tensor FP. Now, actually, there's some interesting literature about trying to kind of define some kind of crystalline subspace of the Galois cohomology of finite Galois modules, and in general, it's quite subtle to do because of various issues to do with Hodge tape weights. For different lifts of this mod P Galois representation, you will get different notions of being crystalline. So this notation actually here of H1F GQT tensor FP is slightly misleading. This crystalline subspace actually depends on the lattice T. Anyway, ultimately, we're only trying to prove a bound on H1F. So we don't necessarily need to come up with exactly the right definition. We just need to come up with some kind of subspace of this finite, of the Galois cohomology of this finite Galois module, such that if we can bound the dimension of that Galois cohomology, it will give us a bound on H1F. So we don't need to have necessarily optimal conditions. And in fact, in this example earlier, where about how many rank 2 genus 2 curves in the LMFDB we can prove finiteness of XQ2 of 2 for, actually the crystalline condition at the prime p equals 2, which is the really tricky one, wasn't even used at all. So anyway, concretely, so in our case, V is the wedge square of this V2 of J. So there's an obvious lattice in there, which is just to take the wedge square of the tape module. And its mod 2 quotient is just the wedge square of the 2 torsion of the Jacobian. So it's a very kind of concrete thing. Then this analog of H1F, again, turns out to be, well, so actually, even at this stage, there's already lots more work to do. So what I did in this work before, in these theorems I mentioned, was I showed that primes of stable reduction, you can make your kind of F condition just be that the class is unramified. In general, that's not quite the right thing to do. And the condition of being crystalline, coming up with the right definition which captures the kind of crystalliness of cohomology classes with values in the wedge square of the full tape module, that's much more subtle in general. Okay, so if we want an analog of this kind of theory of Selma groups of hyperelliptic curves, the first thing we want is an explicit kind of field theoretic description of this Galois cohomology, which is the place that we're going to be doing all our calculations. And again, to ease notation, these assumptions are not necessary. Suppose the Galois group of k acts 2 transitively on the roots of our polynomial f, defining our hyperelliptic curve. Choose 2 distinct roots. And then you take, so then the field obtained by adjoining two. So if our polynomial, say, has degree 2g plus 1, then this field here you get obtained by adjoining two roots. That's going to have degree 2g times 2g plus 1. And there's an obvious involution, an obvious automorphism of that field that you get from swapping alpha and beta. And I just assume that the fixed field under that involution is just generated by alpha plus beta, which is generic. Just assume that Tweed's notation, it's not needed at all. Then the description of this Galois cohomology group is just exactly in terms of units in this field, k of alpha plus beta, whose norm is a square, where the norm goes from k of alpha plus beta to k of alpha comma beta, and then norms down to k of alpha. So I should say maybe, because maybe this isn't emphasized enough in the paper, the fact that you can describe this Galois cohomology in terms of étale algebras is something that was already known, and this was already actually discussed in previous work by the people I mentioned before, who worked on Selma groups of hyperelliptic curves. So this is really just, in a sense, carrying out a calculation, elaborating on the general theory they developed in this example. But what's nice about this example is it turns out to be just about practical to do calculations. So in the case of a genus 2 curve with a rational bias stress point, we're looking at a degree 10 number field. And ultimately, to kind of get a bound on this Galois cohomology once you add local conditions, what you really need is you need to be able to do things like compute class groups and unit groups in that degree 10 number field. And that turns out to be just about doable. Lots of examples. Actually, no, not even just about doable. I mean, in these LMFDB examples, it's very much doable. So there's also a non-abelian x minus t map, which kind of describes, it describes how to kind of get elements of this field, k of alpha plus beta cross, from rational points. So in this case, they won't be from arbitrary rational points because there's no map from rational points of k to this Galois cohomology group here. But it turns out from looking at quotients of the Jacobian that if you have points z1, z2 in x of k such that z1 minus 2 is a multiple of 4 in the Jacobian, then you will get an element of this Galois cohomology of the wedge square, and this non-abelian x minus t map gives a formula for that. And it turns out in this example of this Bijot, Mignot, Six-Sextile, Tengelli curve, that's enough to actually describe this crystalline condition, which you really need. Okay, so now I want to describe some very exciting recent work of my PhD student, Lee Berry, which I think appeared on Archive a couple of weeks ago. So he generalizes, he kind of comes up with a much more satisfactory theory, which first of all removes this description, this condition of having a rational bias stress point. So if you're familiar with Poonen and Schaefer's work, you'll know that even for the kind of abelian theory, if you don't have a rational bias stress point, describing the Galois cohomology of J of 2 is much more complicated. And it's not quite, so you won't get the same description of looking at the kernel of this norm map. It turns out the kernel of this norm map is related to the Galois cohomology of two torsion of the generalized Jacobian. Even then, it's not exactly the same as that. But again, using generalized Jacobians, Lee was able to kind of show how you can at least get bounds on the dimension of this group, and those bounds turn out to be enough to actually prove finiteness of x q2 of 2 for genus 2 curves without a rational bias stress point. And also actually for several genus 3 curves, which was the first time that there's been any kind of like quadratic Chaboty, full fat quadratic Chaboty results for genus 3 curves. I should emphasize again, in all of these results, like this 7,000 LMF curves in the LMFDB result, I think only about in that case, only about 20 of them satisfied the kind of diet quadratic Chabot condition. Um, so this, which is to say that this is really new. So this was one direction in which he generalized things. So the other generalization is describing this crystalline condition. So I said in this one example, using the x minus t map, it was possible to get a description. It wasn't entirely satisfactory because it wasn't clear how it generalized. So what Lee did in this paper was he showed that if you have a curve with good ordinary reduction at p equals 2, you get a very nice conceptual, geometric, and also field theoretic description of this H1F. So the fact that H1F is a more explicit thing for ordinary representations is something which is kind of very known in like subjects like Iwasawa theory, which kind of which have studied these H1Fs in great detail. So what you get is that H1F turns out to, rather than describing it in terms of this complicated, mysterious tetrahedron with B Chris, you just use the fact that you have this map of Galois representations from the wedge squared of the tape module of the Jacobian to the wedge squared of the tape module of the FP bar points, the Jacobian over FP. And so it turns out, I mean, he uses a very explicit description of this. So if you take a smooth model of your hyperelliptic curve at 2 in terms of, say, polynomials H1 and H2, then really you just use the arithmetic of the field, the extension of Q2 defined by H1. Oops. Oops, a daisy. There we are. Okay, and yeah, so he's then able to, so one result he gets is that this just over 1,000 genus 2 curves with Mordell rank 2, good ordinary reduction at 2 and exactly one rational bias stress point, leads 574, satisfy finiteness of xq2 of 2. But even better, he's able to get some examples or in where the rank is even bigger than the genus. So the genus 2 rank 3 curve with good ordinary reduction at 2, for which you can prove finiteness of xq2 of 2. And incidentally, the only way you can do that is essentially by proving exactly the dimension of the Bloch-Kato-Selmer group in question is exactly what is predicted by conjectures. So, and here's a nice example of a genus 3 curve where Magma wasn't actually able to determine exactly what the Mordell group of the Jacobian was. It was rank 3 or rank 4. But either way, it gets finiteness of xq2 of 2. And this is another example where it doesn't have a rational bias stress point. And so, yeah, there's been some very recent progress, and I think there's still lots more still to do on this first question. So next I was going to go on to the second question I asked at the beginning, but before I do that, I'll just pause, see if there are any questions.
Those are great results of your student.
Yeah. Thanks. Okay, so the second question is, now that we've got this, how do we actually compute this finite set? So I mentioned for the usual Chabot-Coleman method, the thing you do is you find this finite index subgroup of the Jacobian, which has rank less than the genus. And then what you do is you compute some Coleman integrals on that finite subset, and you find, by some kind of elementary linear algebra, you find these vanishing differentials. Now, there are, in theory, and this is one of the complications about whether or not this is really an algorithm, because I don't really want to go into this now, but it's not entirely clear that this will tell you exactly what the space of annihilating differentials is in finite time, but in practice it does. And so then you kind of calculate the integrals of these annihilating differentials. So the analog I want is this thing of finding the annihilating differential by linear algebra. So a slightly more maybe instructive example is what happens in diet quadratic Chabot. So there, ultimately, I would say maybe the best analog of this finding the common integrals of your Mordell-Weil generators is computing this thing called the p-adic height pairing, which is a bilinear pairing on the rational points of the Jacobian. So if you, again, let's just assume we have a basis for the Mordell-Weil group. Then you just want to, so you've just got some symmetric pairing, you just want to compute this symmetric matrix. Once you've got that, or some p-adic approximation of that, you can essentially more or less run quadratic Chabati. I mean, there are other subtleties, but more or less that's true. And there's a similar description of XQP2 in general. So this was something I worked out in a paper with Jennifer Balakrishnan a few years ago. And it involves this slightly curious object, which is a bit like a p-adic height pairing. It's called a generalized height pairing. So it's still a bilinear, well, at least for hyperelliptic curves, it gives you something like a bilinear map in the Jacobian, but the target is now a different p-adic vector space. And if you have a rational point on your hyperelliptic curves, it gives you a value of this p-adic height pairing. So in some cases, you can actually just determine the p-adic height pairing by evaluating it on rational points. And so this worked for this curve I mentioned before. But I asked, is this enough in general? And well, I mean, this isn't really entirely satisfactory if we really want to have an algorithm for finding rational points. So I think in a way, I mean, what this tells you is that there's some function, some p-adic analytic function, which is its local generalized height in these local p-adic abelian integrals. And I mean, the way that kind of Kim proves finiteness of these XQPNs under this dimension condition is that you have these transcendental functions which have to satisfy relations on rational points which they can't satisfy generically, and this implies finiteness. But this isn't really entirely satisfactory if we want a method to find the rational points. In a sense, you could argue that this is a bit more like Voigt's proof of the Mordell conjecture. And indeed, many kind of Diophantine finiteness results have a structure like this. You want to prove that you have finitely many rational points. So you're allowed to, so if you kind of conceptually, you can think by contradiction, suppose you have a ridiculously large number, way, way, way more than the Mordell-Weil rank of the Jacobian. Then these points have to have all kinds of strange linearity relations in the Jacobian, these rational points. And eventually, because then so in Voigt's argument, then they also have to have really large height, and then eventually they have to violate these Voigt and Mumford inequalities. You could phrase Chabati-Coleman a bit like this as well. So Chabati-Coleman says that if the genus is G and the rank R is less than G, and you have R plus 1 points, rational points in general position, you get this kind of unlikely relation between their p-adic integrals. And that gives you an equation for XQP1. But that on its own would not give you a method to find XQP1, because typically you might not actually have those R plus 1 rational points in the first place. So what saves the day? Well, this is kind of where the Jacobian strikes back, I guess. Is I said that we wanted to get rid of the Jacobian, but in like, for example, in explaining classical Chabati-Coleman, but there's not really any way of setting up the Chabati-Coleman method in terms of Bloch-Kato-Selmer groups that will still allow you to find this set XQP1, find this annihilating differential, unless you work with points on the Jacobian. I mean, you could work with divisor classes on your curve. So you could work with points on your curve over number fields and then take Galois invariant sums of those p-adic integrals. But that, of course, is just working with points on the Jacobian. And the same is true of Dirac quadratic Chabati. So I give this example, this hyperelliptic curve, which, if I remember rightly, came up in Mesa's program B, where you can find the rational points using quadratic Chabati, but it turns out, if I remember rightly, it only has 2 rational points. And you can't determine this quadratic Chabati function, this function which proves which cuts out the rational points without actually computing the p-adic height pairing on points on the Jacobian, which don't just come from points, rational points on the curve. So it seems like we kind of need a new idea. So just to emphasize that point, because it's quite important, and maybe it's a slightly subtle point, the way that non-abelian Chabati works is that Bloch-Kato conjectures predict roughly that if the Mordell-Weil rank is R, and R is like huge, way larger than G, then Bloch-Kato predicts that XQPN is finite. It predicts that if you have R to the log R over log G points in kind of sufficiently general position, you get some kind of relation between their p-adic integrals, some iterated p-adic integrals, and that relation is basically an equation for XQPN. But as R gets larger and larger, it becomes more and more unreasonable to expect to have this many rational points. So you could try and say, okay, maybe I'll just look at points over number fields and take kind of take rational divisors. So take these analytic functions, evaluate them on these points over number fields, and then sum them over Galois conjugates. Is that going to help me determine the equations? And it's actually not quite clear. So if we go back to the way quadratic Chabati works for integral points on a hyperelliptic curve, say, or even just on an elliptic curve, what this will allow you, if you just apply this quadratic Chabati function, it just tells you the height pairing of a point P with itself. And so if you take that over a number field and sum over Galois conjugates, you're not going to get an element of the symmetric square of the Jacobian, which is the thing that a p-adic height eats. You're going to get something which is Galois invariant symmetric square of the Jacobian over Q bar, which is much bigger. For example, if you take for any quadratic extension of Q, where the rank grows, you're going to get a new piece of this this beast over here. And yeah, I mean, I'm pretty sure you can prove that this thing here is going to have infinite rank, but I didn't actually check this. So just to emphasize, I've got a picture here. So what you can get from kind of evaluating your quadratic Chabati functions on rational points or even on divisors is these kind of, it's going to be elements, say in quadratic Chabati is going to be symmetric squares of things. So it's going to be kind of things which live just on the diagonal. And to compute the full height pairing, you want to be able to kind of evaluate your functions, whether they're p-adic heights or generalized heights, on arbitrary pairs of points on the Jacobian. And that's what I want to kind of describe how to do now in the last 10 minutes. So to describe how to do that, I have to describe a little bit about what the objects involved in non-abelian Chabati are. So they involve these non-abelian cohomology varieties, which I think are can actually be thought of in quite a nice way in terms of thinking about representations of a group, which are kind of block lower triangular with fixed graded pieces. So suppose you've got a bunch of representations V0 up to Vn, and consider isomorphism classes of G representations with a G stable filtration and a fixed isomorphism of the graded pieces with the VIs. So you can actually show that that set of isomorphism classes is a non-abelian cohomology set. It is non-abelian cohomology of a unipotent group. And in fact, under fairly mild assumptions, any non-abelian cohomology set of a unipotent group can be mapped into, can be kind of embedded into one of these kind of sets of isomorphism classes of mixed extensions. So I kind of like to think about this as a bit like mapping a reductive group into GLN, and then kind of thinking of G bundles as vector bundles, or going from passing from G bundles to vector bundles. So let me just give some, I'm only really going to be interested in the case n equals 1 and n equals 2. So for n equals 1, this isn't telling you anything so interesting. So in this case, it's just saying that extensions of V0 by V1 are the same as group cohomology in general, if we're working over a field, we're talking about Galois cohomology of homomorphisms from V0 to V1, so internal hom of V0 to V1. So slightly more interesting is the case n equals 2. So in this case, say I've got representations V0, V1, V2. Then this mixed extension structure, this G-stable filtration with fixed graded pieces, is saying that I can write my representation like this. So these are the fixed graded pieces, look like my original VIs. And the fact that I have this flag, this filtration is telling me that the top bit is 0. And the extension structure is captured by this C1, C2, and C3. So C1 by the argument above is just telling you about the extension of V0 by V1. And C2 is just telling you about the extension of V1 by V2. And then C3 is telling you this slightly more complicated information about how these two one extensions are kind of intertwined to give you a kind of extension with 3 graded pieces. So one thing you can do with that is you can talk about the obstruction if you've got C1 and C2 defining these kind of one extensions, the obstruction to finding a C3. It turns out that giving you a matrix like this, it turns out that obstruction is actually an H2 class. It's the cut product of C1 and C2. And if you have C1 and C2 then, and there is a lift C3, then the set of all lifts is a torsor under this H1 of V0 dual by V2. So I'm going to move to the next slide, but it's okay because I'm just summarizing that with this exact sequence of pointed sets. And this exact sequence of pointed sets is basically how you define these generalized heights. So what you do in full fat quadratic Chabati, well, actually also in diet quadratic Chabati, if you use the kind of Nekovar formulation of it, is you associate to rational points certain mixed extensions with 3 graded pieces. And then you construct certain nice functions, which are called generalized heights or p-adic heights in the diet setting, on spaces of mixed extensions. And the way they work, those functions work, is essentially that locally, almost all primes, the set of mixed extensions with graded pieces QP V, which is the Tate module, and the tensor square of V, is actually just the same as extensions of QP by V tensor 2. It turns out the C1 and the C2 don't really contain much information. So this gives you a bunch of elements in this now. So you started with something very non-linear, and now we actually have something in this QP vector space. And basically that's how you define the generalized height. So there's a minor subtlety, and it turns out if you quotient out by the kind of global V tensor 2, then you get something which is really bilinear in its arguments. But there's a subtlety, which is that it's not clear that it defines a pairing because it's only defined on the kernel of this cut product map. And there's another subtlety, which is also not clear how we compute it. So let me explain what I want to do. So remember, to be able to compute quadratic Chabati sets, we want to be able to compute this pairing. That's essentially the main kind of stumbling block. And one way we could do this is by trying to find more mixed representations, which are geometric, which come from geometry. And so these mixed representations, they don't come from Étale cohomology of projective varieties, but they should come from Étale cohomology of open varieties. And in fact, the ones which come from rational points, there's a very beautiful formula due to Beilinson that explains exactly what the Étale cohomology in question is. And so I guess maybe the main result in part 2 of this talk is that the Beilinson block conjectures on algebraic cycles imply that the generalized height pairing is actually a pairing, at least if you restrict its source to the subspaces of Galois cohomology which come from algebraic cycles. And that should be a CH1 excellent. Sorry. So 2 should be a 1. I'll say a little bit more about that in a second. Just about to wrap up. So to summarize, this is kind of the computational problem really that I think involving algebraic cycles, which I think is interesting. We want to find these mixed representations, or essentially these algebraic cycles, these, mixed motives, which will give us the mixed representations, which will allow us to compute the generalized height. So you could think of this as a bit like having a motivic version of quadratic Chavaty in a way. And a big inspiration for this is the motivic version of Dyack quadratic Chavaty, which was developed by Edixhoven and Lido. And essentially the kind of, if I take my mixed objects, my graded pieces to be QP, V, and QP1, then the motivic avatar of this space of mixed extensions is the Poincaré torsa, which is some GM torsa over the product of the Jacobian with itself. And in some sense, you really use this when you compute the p-adic height pairing. I mean, you're really working with the Poincaré torsa, even if you're just, maybe when we compute it in practice, we think we're just working with pairs of divisors. That's often how you compute p-adic heights. It's evaluating them on pairs of divisors. So this is in many ways a kind of an inspiration, but in some ways it's misleading because the fact that this was a scheme is very special to the Galois representations we chose. That's because there's this very powerful theory of rational homotopy theory of complex algebraic varieties, which tells you which unipotent groups can be fundamental groups of complex varieties, and it turns out the answer is not very many. So if we expect to have some kind of motivic avatar of these spaces of mixed extensions, we kind of can't really expect it to be a scheme anymore. And I'm a pretty simple-minded person, so I'm just going to take it to be a set. So I've given an example here of how this is done for the S-unit equation, although people maybe don't tend to phrase it this way, but for reasons of time, I'm going to skip this example. So in this case, it turns out to be related to Suslin's work on the block group. For rational points on curves, what we're more interested in is zero cycles on the product of x with itself, so on a surface, which are trivial inside the Albanese variety of x squared. So this is called the Albanese kernel. The conjecture of Beilinson block, which we're using, is that this is finite when you have a curve over a number field, and it turns out that that implies that you can compute the generalized height pairing. I have a few more slides about that, but I don't think I'm going to say any more about how that works. But just maybe give an example. So here's an example of, sorry, it should be an equals there, f of x equals. So here's an example of a curve with mod of a rank 2, and it has 5 rational points that we know of. And so you can compute this generalized height on these points here. So to actually compute the generalized height in general, you need to be able to compute this pairing with the 2 distinct points of infinite order. And it turns out it doesn't seem that you can do this by evaluating rational points or points over number fields. But what you can do using algebraic cycles is you basically find curves inside x plus x and principal divisors on those curves, on which you can, which allow you to compute the generalized height of your original base curve. So in this case, we take this bihyperelliptic curve, this principal divisor, which is defined over a degree 8 extension of Q. And it turns out that this, some calculations show that this actually allows you to compute the pairing. And so finally, I mean, I think there are lots of other questions, which are, maybe some of them don't make so much sense. But one question maybe I want to particularly emphasize is that here I did that calculation over x plus x, but perhaps it would be more clever to be working over the Jacobian or even over its Kummer variety. So this is, again, an explicit computation now on a K3 surface, which was something I mentioned earlier. Anyway, thanks very much for your attention. Thank you.